Welcome back. So today let us continue with our discussion on the relaxation phenomena and how to measure them. And of course, in the last class, I was trying to work out and try to give you the conceptual understanding of what is a spin lattice relaxation. Basically, concept was like this. If you have not followed or if I miss some points, because I know relaxation is a fairly a tough topic to understand. Let me tell you. As soon as before putting the sample in a magnetic field, there is a no net magnetization. Put the sample in a magnetic field, there is net magnetization. Why this net magnetization came? We worked out taking into account the possibility of transition probability from alpha state to beta state and beta to alpha. And of course, logic says transition from beta to alpha should be more than alpha to beta because there are more spins in the ground state than in the excited state. When we put this into this equation and try to understand, we found out at thermal equilibrium n alpha is equal to n beta. That was not agreeing with the our conceptual understanding. So as a consequence, we brought in the concept of deviation from equilibrium. Magnetization deviation from equilibrium or deviation of population from the equilibrium in both the energy states and work out the deviation of magnetization. Then we've understood for the magnetization to attain to thermal equilibrium from deviation to come to the thermal equilibrium, original magnetization, then we know there was a time constant called T1. This T1 is a mechanism, I said, is a relaxation phenomenon, a time constant, which makes the spins to attain thermal equilibrium. Come back to longitudinal magnetization along Z axis. That's what we call spin lattice relaxation, longitudinal relaxation, attaining thermal equilibrium, thermal relaxation, lot of synonyms are there. Okay, that's what we said. And we also understood because there's a more probability of the spins aligning along this axis in a direction parallel to the field than in a direction opposite to that, there must be some energy loss in the system. Energy has to be given out. Where does it give the energy? How does it give the energy? We understood the energy is given in the form of heat to the surroundings. What are the surroundings? Anything other than this nuclei of your interest, other than your spin, like any of the surrounding atoms, nucleus, molecules together, the entire surroundings, external surroundings, we call it as lattice. So it gives energy to the lattice. That's what we said. So how does it give the energy? What is the requirement for that? There must be some fluctuating fields whose frequency should match with the larger frequency. And this fluctuating should be in the transverse plane so that it is giving the energy. So this should match with the larger frequency. Then the excited spin will give energy to the lattice and come down. Okay, to come to the thermal equilibrium. Lattice, of course, gets energy. When it gains energy, it gets this energy has to be given to the system. It is given in the form of a heat, small amount of heat, which in the body temperatures, this energy, this heat is much smaller than the kinetic energy. Okay, so what the kinetics which takes place is much smaller. So we can largely ignore it, goes unnoticed, and this loss of energy is not recoverable at all. These are the important concepts I said. Now I also said there must be a source of fluctuating field without which spins cannot relax, and the source must be something else. What is the source? The source of fluctuating field must be some other proton, some other electron, or any other nearby molecule. And it is necessary to induce relaxation. If there is no fluctuating field, spins do not relax. Okay? You will understand that later. For example, when we study solids and liquids, there is a vast difference in the T1 because the fluctuating fields are more and the molecules undergo a lot of motions in the case of solution. The T1 is much shorter compared to solids. Sometimes solids, it is a general statement, need not always be true. Solids, sometimes the relaxation time can be order of minutes, hours, and days and weeks. Whereas in solution, most of the time, the relaxation time will be of the order of few seconds or minutes, a few tens of minutes. Okay. So remember, when you applied a radio frequency field to excite the nuclear spins, we need to have a fluctuating field. I mean, sorry, oscillatory field in a direction perpendicular to it, perpendicular to the magnetization, which is along thermal equilibrium. That's what I said. Only then you will perturb the system. Okay, so you have to perturb the system to detect the NMR signal, and this perturbation frequency must be at the Larmor frequency. That's what I said. That's why we apply a radio frequency pulse at the Larmor frequency to bring the magnetization from z-axis to transverse plane. Now, similarly, the RF fields, which is caused because of the fluctuation here, must also be in the Larmor frequency at the Larmor frequency in transverse plane. Please remember this point. Now, what is the difference between this and that? B1 field excites spin, whereas fluctuating fields relax the spins. Both we say at the Larmor frequency. What is the difference then? Remember, B1 field is where radio frequency pulse applied to excite the nuclear spins. That is, perturb the magnetization from thermal equilibrium to bring it to transverse plane. Fine. But we also have a fluctuating field now, which comes whose Larmor frequency is also in the whose fluctuating frequency is also at the Larmor frequency. This enables the spin to relax. Then what is the major difference? The major difference is the RF field which you apply to excite the spins affect all the spins uniformly. Remember, the uniform excitation is done by applying the radio frequency pulse, such that I told you about how to choose the region for uniform excitation, everything. I hope you all remember that. Whereas the fluctuating fields are local, they're random in magnitude and affect only a few spins. It doesn't affect the entire system. Whereas the B1 field affects the entire spins uniformly. This is a basic difference. Please remember that. Okay, with this, let me give you some idea about the relaxation, T1 relaxation. Some important points for you to take home. One is T1 is a constant, as a time constant for magnetization to grow along z-axis. There are several terminologies for this, like spin lattice relaxation, thermal relaxation, longitudinal relaxation, various things. But all remain same. The conceptually, everything is same. It is only naming in a different way. And it requires energy transfer from spins to environment. That's anything surrounding that spin, that is the external environment, is called lattice. Okay. Next. This energy transfer must be stimulated. Spontaneous emission is not possible in the radio frequency region. How do you get the stimulation? Its stimulation is obtained by transverse field fluctuating near the Larmor frequency. And what is the source of fluctuating field? It is again the molecular motion of a nearby proton, electron, or some other atom nearby. All this fluctuation gives us to frequency, which is the Larmor frequency. Only then the spins can relax. These are the summary of the points. So far I was telling you about T1. Okay, let us now go to another topic called T2. T2 is the relaxation phenomena, time constant. What is T2? Remember, when you bring the magnetization from z-axis to xy plane, we discussed extensively in earlier classes. Instantaneously when the magnetization is brought, there is a phase coherence. All the magnetic moments are along the x-axis, along the axis in which you have brought the magnetization. There is a phase coherence. But then what happens? Because of various phenomena, the spins starts losing coherence, losing phase coherence. So slowly they start moving, some in a different frequency, some moving faster, some moving at a lower frequency, some moving at a faster frequency. They start dephasing. Slowly they start dephasing. When they start dephasing, when you start collecting the signal, if you have a receiver here, immediately when there is a phase coherence, there is a maximum signal. When the coherence is, when the spin start decoherence starts, the signal intensity keeps coming down. When there is a completely spins undergo decoherence, then what is going to happen? In the xy plane, there is a random phase of x1, y component. This is a random phase approximation. As a consequence, you don't see any magnetization at all. But when it is dephasing, simultaneously, it is also growing along z-axis. That is what is required, and that is a T1. But for the complete dephasing to take place in the transverse plane, it has a time constant. The magnetization X and Y component decay or dephase with time. That is called T2, relaxation time. This also is a relaxation process. If you understand, this is relaxation is nothing but the dephasing of the spins in the transverse plane. And T1 is growth along z axis. The one is along X transverse plane, other is along longitudinal axis. And this also has synonyms. You call it transverse relaxation or spin relaxation. Does not matter. So now you know there are two types of relaxation. One, the spins will gain energy and will lose energy from a perturbed state. You have given energy and perturbed it, and then slowly come back and attain thermal equilibrium. That's one thing. The time constant for is T1. The spins which were brought to the XY plane, there was a phase coherence immediately, and slowly it start decaying with time. And after some time, when there is a complete decoherence, you will not see any signal. That is called relaxation in the XY plane. This is called transverse relaxation. And it has a time constant called T2. So these T1 and T2 are the two different phenomena. One is a growth function, other is a decaying function. In the X-ray plane, the signal decays. You will slowly, the signal intensity starts coming down as it undergoing decoherence. But slowly, the signal intensity starts going up along z-axis because with the time constant, it starts coming back to equilibrium. So one is a growth function, other is a decay function. Interestingly, both of them are exponential. One is a exponential decay, other is an exponential growth. And after some time, the initial Boltzmann distribution along Z is preserved. The initial value of M in the Z direction immediately before the RFS has been converted to net. And the presence of non-zero this thing is called phase coherence. Non-zero net transverse magnetization is called phase coherence. And it is a temporary statistical phase coherence. Remember, temporarily there is a statistical phase coherence in the X-ray plane. And the process which disrupt this phase coherence either the number or the relative positions of the transverse components will result in what is called T2 relaxation. There can be some number of processes. I'll tell you as we go ahead. For the spins to disrupt this type of coherence. Okay? How it disrupts? It disrupts the phases, the relative positions of the vectors. So it makes it to undergo decoherence. And this process will finally make sure the transverse component, this will result in transverse component going back to complete decoherence called T2 relaxation. So simple logic is this. Bring the magnetization along XY plane by applying a pulse. The loss of phase coherence leads to loss of signal. That's what I was telling you. Simple logic, if you don't understand magnetization, components, etc. Bulk magnetization is here brought to XY plane. Instantaneously, there is a statistical phase coherence. Okay, that's what I said. Remember here, temporarily there is a statistical phase coherence. And this phase coherence is getting lost by some mechanism. And that time is called, time constant required for that is called spin relaxation T2. That's all you should understand. And as I said, this is mx and my component, you call it as m0 into this one, decaying function. M0 is initial magnetization, okay, thermal equilibrium magnetization. And after some time, you see that when you give enormous amount of time, after some time, this will go to 0. And then mx and my, there is no component at all, there is no magnetization. You will not see any magnetization in the mx and my component. And this is the diagram which tells you how the phase coherence takes place. Apply 90-degree pulse, bring the magnetization to this place. And then spin starts undergoing decoherence here. Initially, there is a full magnetization, complete intensity is there. Intensity is maximum at this point because there is a temporary statistical phase coherence. With time, slowly the phase coherence is lost, signal intensity you start losing. And after some time, it so happens there is a complete decoherence. There is no signal seen in the transverse plane. There is no component at all. This constant is time constant, which makes this component of the magnetization mx and my to decay completely or to undergo decoherence completely is called T2. Okay, spin relaxation. Now T2 relaxation you will always accompany T1 relaxation. Remember, T2 relaxation always accompany T1 relaxation because T1 relaxation occurs when a spin exchange energy takes place with its surrounding. When such an energy exchange takes place at any time, if it affects only one of the spins, any one of the spins, which is contributing to magnetization in the X-ray plane, then that also gets, what will happen? This both transverse and longitudinal component gets affected. They will also start getting changed randomly. As a consequence, when T1, while the energy exchange is going on, if affect any one of the spins contributed to MXY, then it helps in losing phase relations with other spins. So this also helps in T2 relaxation. So that means T2 relaxation always accompany T1 relaxation. Is it true all the time? Is the next question. Of course, most of the time, any process that causes T1 relaxation also causes T2. But, and I tell you later, there can be T2 relaxation without T1. This is sometimes called T1 contribution to T2, or in other words, they use a technical word called T1 in T2. Okay? This is a T1 contribution to T2 because any process that causes T1 relaxation causes also T2 relaxation. T1 relaxation occurs, T2 relaxation without T1 also. That's what I said. T1 relaxation causes T2, but T2 can happen without T1 also. For example, most of the time, T2 relaxation accompanies this. Sometimes without T1 it happens. This is referred to as secular contribution to T2. It's a technical word. Don't worry. Remember, when T1 contribution happens to T2 relaxation, there is a T1 contribution. That is called T1 in T2. This is called T2 happening on its own without T1 is called secular contribution to T2. Okay. So T2 relaxation occurs without this thing. In some situation where what is called dipolar interaction is there, where two spins at a time undergo transition from alpha beta to beta alpha. This is called flip-flop term. When a flip-flop term is there, like alpha beta going to beta alpha simultaneously, such type of transitions which causes what is called T2 relaxation without T1. Okay, so these are all more details, but remember T2 take home message is T2 is a time constant for decay or dephasing of transverse magnetization in the XY plane, that is MXY. Synonyms for it: transverse relaxation, spin relaxation, and it can occur with or without energy transfer. Okay, with T1 or without T1 it can happen. And anything causes T1 relaxation also causes T2, but T2 relaxation can independently also occur without T1. Please remember this point. This one is called T1 in T2. This is called secular contribution to T2. So major causes of T2 is to defocus, for the spins to undergo dephasing is a statistical local fields. That is the major cause. Okay, this is the T1 and T2 processes. Remember, these are the T1 and T2 processes. Graphically, I am showing you T1 is a growth of magnetization, T2 is a decay of magnetization. Both of them follow exponential function. Okay, they both of them are exponential. This is an exponential decay function. This is an exponential decay function, growth function. See, m0 into 1 minus e to the power of minus t by t1. Okay, so when it totally becomes 0, m0 is equal to m0. There is a complete thermal equilibrium is achieved. Here you can see after a long time of T2, there is no magnetization at all. Totally keeps decaying. After a long time, when T2 becomes enormously long, MXY becomes 0. When T2 becomes more here, you can find this becomes smaller and becomes 0. So one is a decay function, other is a growth function. Both are both follow exponential function. Please remember that. So sometimes you use terms called relaxation rates and relaxation times. What is the difference? Relaxation time is the time which you measure, T1 and T2. Is a time constant. The relaxation rates are inverse of that. Sometimes they call it R1 and R2. R1 is inverse of T1, 1 over T1. R2 is inverse of T2. So R2 is nothing but 1 over T2. R1 is 1 over T1. They are called relaxation rates. And T1 is called relaxation time. So relaxation rates and relaxation times are related like this. Relaxation times rates is nothing but inverse of the relaxation times. Okay. So why T1 is always longer than T2? Of course, don't worry about that. Now, what is the size of the T1 and T2? If you want to see, look at this. This is a function which explains as a function of molecular tumbling, which produces fluctuating fields and enabling relaxation processes. If you look at this is a graph. Small and rapidly rotating molecules like small free water, small molecules has a very long T1 here. You see, T1 is very long for small molecules. Okay. And if you go to relaxation rate, it is a faster because longer relaxation rate means inverse of that. Rate is faster. On the other hand, like big molecules, there is a slow motion, like proteins and dense solids. Molecular motions are very slow. In which case, T2 gets shortened, and but T1 increases. Understand? For big molecules and solids which undergo slow motions, T1 is very large, T2 is very short. Whereas for small molecules, okay, like this, which undergo rapid motions, rapidly rotating molecules, both T1 and T2 are longer. This gives you an idea about the size of the T1 and T2 depending upon the size of the molecule. Okay, T1 and T2 depends upon size of the molecule and the molecular motions, tumbling motions that is going on. So this is not necessary. But causes of relaxation, I said, a successful relaxation mechanism requires two conditions. There must be an interaction which works directly on the spins. The interaction must be time dependent. That's what I said for both the phenomenon. All right. So this we discussed already. It has to be interaction it has to be time dependent fluctuating field so that interaction has to take place. This cannot be static. It has to be fluctuating magnetic field, and the time dependence must be suitable NMR time scale at the normal frequency. That's what I discussed. And because it should be at the NMR time scale, and this can molecular motions like vibrations, electronic motion, such type of motions will not affect NMR relaxation. Only some molecular rotations and diffusions are the things which are very important for sources of relaxation. Please remember, for the relaxation process in liquids, molecular rotations and molecular diffusion are important. That is the one which causes, which helps in relaxing. Okay, this of course we have been discussing again and again. Thermal motions in liquids cover a wide range of frequencies, and all of them will not contribute to this. There is we have to discuss about the spectral density function and everything, and the molecular motion we have to define correlation function, tau c, etc., which we discussed to some extent in the NO even we discussed. We let us see this. There are several relaxation mechanisms. Each and everything can be discussed for hours and hours. One is dipole-dipole interaction. This is a major source of relaxation. Chemical issue anisotropy is a major source of relaxation. And molecular translation, flow diffusion, chemical exchange, scalar coupling, electrical quadrupolar coupling for spin greater than half. There are various mechanisms. All these phenomena which is happening in the molecule, in the sample, can give rise to mechanism for relaxation. But dominant are dipole-dipole and chemical anisotropy interactions. So if you visualize the T1 and T2 processes together, they are not exclusive processes. I have been telling you even earlier also while discussing NOE, I said these are all processes which takes place simultaneously. And this is what you have to imagine. I showed this earlier also. As the magnetizations start dephasing in the X-ray plane, simultaneously it starts going along z-axis. So it looks like it is undergoing a spiral like this. So T1 and T2, if you visualize, simultaneously it is happening. The magnetization goes like this. It's a huge magnetization initially, full magnetization. There is a statistical phase coherence, maximum intensity of the signal. Slowly, when it undergoes dephasing, reduces, and afterwards keeps reducing in the X-ray plane, but keeps growing along the z-axis like this. This is the combination of T1 and T2. If you view together, this simultaneously is happening. This is the path it appears to take. Of course, T2 is a very easy to find out. Inverse of half of the line width, find out the line width at full width at half height, and inverse of that with pi into inverse of that, this thing will give you T2. Also, full width at half height is equal to 1 over pi T2. Very simple relation. So if I measure the line width, I know what is T2. Approximately, I can tell you what is T2. So if you understand everything, remember in this is a relaxation. Although it undergoes transition between the energies, there is exchange of energy between the spin's energy state and the lattice. It is a radiationless transition. It is not a transition which you detect. It is radiationless only to aid the spins to relax. Okay? It is not the transition that you are going to detect. And of course, longitudinal magnetization, I explained what happens. Which is the recovery of magnetization and all those things. There is no need to discuss again and again. Now let us see measure T1 and T2. These are the two important experiments. One experiment I will tell you how to measure T1. T1, there are several experiments to measure. What is called saturated recovery, and you can saturate the spin system first by applying continuous radio frequency pulse and see how it recovers, how much time it takes to recover. That is one way of getting the T1. You can get T1 at the null method. There are 5 or 6 methods of measuring T1. You can see in the literature is available, and there are all the methods we don't need to discuss. But the commonly used is inversion recovery sequence called T1. Of course, there is another one is called progressive saturation. Keep on applying the pulses one by one progressively, one after the other. Every time you collect the signal and see when it gets saturated. So that is progressive saturation, saturation recovery, null method, and inversion recovery. The inversion recovery is a very interesting thing. What you do is first apply a 180-degree pulse on the signal, magnetization. 180 will bring it to minus z axis. And if you have a signal here, okay, if you have a receiver here, you get negative signal. Okay, you are not going to see any signal here. It appears from z axis, you get minus z axis. Magnetization comes to minus z, you get a negative signal. And this one, after 180 pulse, gives some delay. And then magnetization would have slowly grown, going back to z axis. Keep on varying this delay. At every interval of delay, start collecting the signal. See how the magnetization is growing. And then this is, I said mz equal to m naught into 1 minus e to the power of minus t by t1. T is the variable delay here. For different values of t, you calculate this and do a curve fitting. Like simple thing. First you bring the magnetization but to minus z, signal is negative, slowly keep reducing and then keep going along z axis. This is the inversion recovery sequence. First, magnetization is brought to negative axis, phase decoherence takes place, magnetization intensity comes down, becomes zero. This is called a null method. If you find out what is the time required for the signal to get nullified in 190 tau 90 sequence, this tells you this is 0.693 times this t value, time is the t1 value, because you put into that equation, okay, mz equal to m naught into 1 minus e to the power of minus t by t1, fit into that equation. When this term goes to 0, you can find out exactly at this point. If you find out it is a logarithmic value, you can find out it turns out to be 0.693 into the time period gives you t1 in this point. There is a null method. Goes further up, becomes positive, 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 and completely comes back to thermal equilibrium. Now, each time you measure the T1, each intensity for each delay, and then do the curve fitting for the exponential function what you are using for measuring T1. Fit into that equation mz equal to m naught into 1 minus e to the power of minus t by t1. For in this inversion recovery, it is 1 minus 2 times e to the power of 2 into e to the power of minus t by t1. Okay, that equation y2 comes, you can see later. It is simple mathematics. This is how inversion recovery works. For example, a toluene molecule, first invert the signal. There are three types of proton, benzene protons and CA3, and this is TMS. See, it inverted here, slowly start getting the signal positive, maximum. And this one and this last one should have equal intensity. That means the thermal equilibrium magnetization was brought to minus Z, slowly it goes back and go to original equilibrium. You see, this, if you fit this data points into that exponential equation, you will get the T1 value. Same way you can find out for the CA3. So for each spin or each peak, you can get the T1 individually by inversion recovery experiment. Please remember, you can measure the T1 by inversion recovery experiment. This is very useful for you because you can understand dynamics of this molecule. Of course, these are all some of the few examples. Different spins of the same molecule can have different T1 values. Okay. See, in this case, see, this is the null method. If you do the null and find out what is this T1, you can find out what is the T1. Okay. If they sometimes we adapt a trick called, if the system is a very, very long T1, use material called a lanthanide shift reagent called a paramagnetic relaxing agent called chromium acetyl acetate. It's not lanthanide, that is different one. This is a chromium acetyl acetate. Microgram quantity, very little you add it. It will enable the spins to relax. See, this is without Krakow, these two peaks have very weak intensity. Now they are relaxed and you get better signal. So these are called relaxing agents. Krakow, it is chromium acetyl acetate. It is used to, it is a paramagnetic relaxation reagent used to reduce the relaxation time. Please remember this. Okay, now we can go to the similarly, spin echo method is what is we adapt for measuring T2. Spin echo is, I have already discussed in depth. We vectorially also we understood. The inversion recovery is 180 tau 90. Spin echo is 90 T1 by 2, 180 T1 by 2, or 90 tau, 180 tau, and collect the signal. But here it forms a echo like this. You have to collect the signal how in the top of the echo how it is decaying. This is echo amplitude. And this decay of the signal when you are collecting the signal as a function of echo amplitudes, you can fit it in exponential again, you will get T2. Because this echo amplitude decays as a function of T2. You understand how you can measure T2? Simply remember, spin echo sequence is what is used. It is called Kahr-Purcell spin echo. The improved version of that, you can have a multiple echoes. Of course, this is what we discussed about spin echo, how it differs everything earlier. So, okay, this is a Kahr-Purcell echo. In the realistic experiment, you do this, after some time, apply a 180 pulse, see it goes back and forms a echo here. Fantastic, this is echo peak. And how it decays as a function of echo, if you have a number of echoes like this, it is exponentially decaying. Fit this echo amplitude to the decaying function which I gave you earlier, then you can get T2. And you can have multiple echoes. These are called, not in the one experiment we had only 90 tau and echo here. But to see how it is decaying, you can have multiple echoes. Keep on doing the echoes like this. Keep on applying one, see, bring the magnetization from 90 into x-axis. Apply 180, take it here. It will start dephasing. Apply 180, bring it here. Like that, you can keep on applying n number of times. Every time you can start getting the echo. And the echo amplitude, you see, reduces exponentially. Can you see it here? It is reducing exponentially. And this is what you have to fit the curve for that equation of decay function I gave you. Then you can measure exact value of T2. Of course, this has a contribution in inhomogeneity, various things we discuss. It is not a original T2. This comes because of the contribution from magnetic field inhomogeneities also. That can also cause signal to decay. Then you have to subtract that component. So there are several tricks adapted. And anyway, I will not go into all those details. But basically, remember, If you want to, I gave you the idea about what is T1, what is T2, conceptual understanding, what is a growth function, what is a decay function, everything we discussed. T1, if you want to measure, you have to adapt inversion recovery method, that is 180 tau 90 sequence, vary the tau value, and keep on collecting the signal as a function of tau, and then intensity of the peaks you get, fit it into that growth function. For measuring T2, you adapt a spin echo sequence. You can have a multiple echoes like Corpus or Maybach-Mugil sequence, and you get the echo amplitude. That is a decaying function again. Measure the echo amplitude at every echo and fit it into the decaying function. Then you get T2 value. Of course, there are lots of corrections to be applied, everything which I did not discuss because this is not a original T2. This T2 is has contribution of field inhomogeneities, many things you have to subtract and make apply corrections, everything. Those details I'm not discussing, but I'm just giving you the gist and idea of how to measure T1 and T2. Okay, I stop at this place, at this point now. I have told you in last class and this class lot about T1 and T2. Of course, because of time constraint, I had to go hurry because already I have exceeded number of weeks given to me to teach NMR. My number of classes are already over. Still, I have to teach lot more. So I went little faster this in this class and last class. But nevertheless, I gave you the idea. I'm sure, however fast I'm speaking, I'm giving you the concept. If you are attentive, I'm sure you would have got the points. So we will stop for the relaxation time and concepts and measurements for this class. We'll go to the next topic in the